Very good afternoon to all of you. Today I am present here for discussing the IV characteristics of thyristors. So before moving ahead on the IV characteristics of thyristor, we have to understand certain things. Certain things should be very clear, and then only we can move ahead. First of all, thyristor, or as the name suggests, SCR, silicon controlled rectifier. What an SCR is, why it is useful, what are its functions. We have to emphasize on this part first of all. So thyristor is basically a device that is used for controlled power flow. It is used for controlling the flow of power, okay, as desired. First part. Second part is that it is used for providing the controlled inductance or the controlled capacitance. It means a thyristor can be very helpful if controlled properly in creating a reactive power source which consumes reactive power and also which supplies reactive power. I think these things are quite clear. Now coming back to the SCR basic formation, it comprises of anode to cathode junction with a gate J1, J2, J3, P plus, N minus, P and N plus. Okay. The P plus region is the topmost region. You can see it is quite visible here. This is the region P plus where the junction J1 is situated, and it will have a carrier density of 10 is to minus 10 is to power 19 centimeter cube. It means 10 is to power 19 p-type elements per centimeter cube are present here. Okay. After that, the N minus layers or the P layer, the medium doped, the lightly doped and the heavily doped. So the lightly doped region will have 10 is to power 14. Yes, 10 is to power 14 carriers per centimeter cube, and a mediumly doped region will have a carrier concentration between something 10 is to power 16 or 10 is to power 17. Okay. Now it is very well understood that the donor atoms or the donor atoms will be majority charge carriers for, they will donate their electrons, so they will become holes. Okay, so it is very easy and very simple to understand that once they donate their electrons, then they will become holes, or we can say that they will get neutralized. Okay, so they will form the N minus layer and the acceptors. Okay, so donor atoms will provide the minority carriers in the p-type, while the donor atoms will be majority carrier providers in the n-type. This is quite obvious, because the donor atoms will donate their electrons. So when this donated electron gets absorbed by a different atom, okay, then it will form the n-type signal. It will become in itself the n-type carrier. Okay, so it will be the majority part in a n-type semiconductor. Now this gate, when the current is passed through this gate terminal, then it will facilitate the flow of current, and the current will flow from anode to the cathode. How? When the current is given from this gate terminals, or we can assume if the positive flow is from gate to cathode, then electrons will flow from cathode to gate. These electrons will not only flow to gate, but these will also go towards J2, J1. Now look at this junction, P plus N minus. This is having positive ions. Now when a forward bias is applied here at the AK, then junction J1 is forward biased, junction J3 is forward biased. PN junction both are forward biased. Only junction J2 is reversed biased. So this junction needs to be broken. The reverse bias nature of this junction needs to change. How it is changed? It is changed by the inflow of these currents. These electrons will come. These will go and combine with the positive side of N minus. And similarly, these electrons will attract more holes from P plus region, and these holes will damage the N minus region of, or N minus ions of P region. So a small current will be set up. As we increase the gate cathode density, the gate current voltage, then subsequently the current flow will go on increasing, and as the current flow will increase, a current is set in the thyristor. Now that current, once the thyristor is switched on or turned on, is now controlled by load. After the turn on of thyristor, the gate loses control over the device. As the control is lost, due to the loss of control, we can simply conclude that two things are clear. The off time cannot be controlled. Yes, the off time cannot be controlled. And second thing is that only the on-site current will decide the conduction of thyristors. Have a look at this point. IV. Okay. Now this is the IV characteristics of a thyristor. When the voltage is up to the breakover voltage, VBK, the breakover, okay, then the current will increase very slowly. Slowly the current is increasing. Okay, very slowly. Voltage has increased quite a large bit, but the increase in current is very small. This is the forward blocking region. This is termed as the forward blocking region. I think I am quite clear up to this part. After once the forward blocking region is covered, then if further increase in the gate voltage, in the VAK voltage is done, then in a brisk time the voltage will immediately reduce, and the device goes into conduction. So when the device goes into conduction, then the minimum current that has to be set in the device so that the device conducts is termed as the latching current, that is IL. Okay, so IL is the minimum current that has to flow through the device so that it goes into the conduction. IH, holding current. Holding current is nothing but the current below which the device ceases to continue. The device doesn't conduct. It is termed as the holding current. I think this point is quite clear, that the role of latching current and holding current are quite clear. Now have a look at the negative part, that how the voltage controls the current flow in the reverse direction. It is simple and it is quite similar to what we observe in a diode. As the voltage is increased, a very small amount of leakage current will flow, and when the voltage is kept on increasing, then suddenly the device current increases in the reverse direction and the device burns off. This is the schematic diagram of a thyristor. A to K are shown and the gate terminals are quite visible. The various layers and the junctions and their bias in the forward direction, in the forward applied voltage, and the negative applied voltage is also quite clear. So in this lecture I had totally explained the working of thyristors. We will study more about this in the upcoming lectures. Thank you.